Microscopy is the study of samples with the aid of a microscope that can otherwise not be seen with the naked eye. Two main classes of microscopes exist, namely light microscopes, which uses light as a form of radiation, and electron microscopes that uses electrons as a source of radiation. Now, light microscopes can further be categorized into simple light microscopes that only uses a single lens, like a magnifying glass, and compound light microscopes. Electron microscopes then include scanning and transmission electron microscopes. The two most important qualities when working with microscopes are magnification and resolution. Now, magnification can be defined as the number of times an image is larger than the specimen being observed. This can be calculated by dividing the size of the image by the size of the specimen under your microscope. You can remember this by remembering I am, which means magnification equals image over the actual size. Then we have resolution, which can be defined as the ability to distinguish between 2 points that are close in proximity, meaning that the higher the resolution of the image, the more details will be observed. This is highly affected by the type of radiation that is being used. Light waves, which are made up of photon molecules, have a wavelength spectrum of 400 to 700 nanometers. For us to be able to see an object, it must interfere with the particle in a wave. When this interference happens, the wave will be reflected back and an image will be seen. The general rule of thumb is that an object needs at least half the size of the wavelength to cause an interference. This would mean that the smallest object or resolution that can be observed with a light microscope is 200 nanometers. Now, electrons are also particles that move in a wave format with a much smaller wavelength of 2.2 to 3.8 picometers. 1 picometer is equal to 1 times 10 to the negative 12 meters. This means that if electrons are used as a form of radiation, much smaller objects would be observed. Now you might be asking, why not use X-rays or gamma rays, as they also have a much shorter wavelength? Well, this was attempted but failed, as these type of radiation was very difficult to focus, whereas electrons, being negatively charged, could easily be focused using magnets. Magnification and resolution is highly dependent on each other. You cannot have a high magnification with a low resolution, as this will only result in a blurry image. Let's have a look at the light microscope in a bit more detail. The light source is placed at the bottom of the microscope and will produce a beam of light moving upwards. The beam of light will first move through the iris diaphragm that has an adjustable slit to make the beam narrower. It will then pass through a condenser lens that will focus the light onto the specimen. After the light has passed through the specimen, it will move through the objective lens as well as the eyepiece lens. Both lenses will magnify the image. Thus, if you want to calculate the total magnification, these two magnifications would need to be multiplied. Now, if we were to look at a general animal cell using a light microscope, we would be able to observe the cell's surface membrane as the boundary of the cell. Remember, the cell membrane is 7 nanometers in diameter, so it will not be seen as a separate structure. We will also be able to see the nucleus, including the nuclear membrane, nucleolus, and chromatin. We would also be able to see the Golgi body as well as the general shape of the mitochondria. If we had to observe a general plant cell under a light microscope, we would see some additional structures, including the cell wall and chloroplast with the grana just visible. To be able to observe more detail, we would have to use an electron microscope. Now, unlike light beams, electrons cannot be seen. Thus, to be able to observe the image, it will need to be projected onto a fluorescent screen. Another difficulty is that if electrons collide with air molecules, they would scatter and an image will not be able to be produced. Thus, the flow of electron beams would need to flow through a vacuum. At the top of the electron microscope is an electron gun and anode. The electron beam will move downwards through the electromagnetic condenser lens that will focus the beam of electrons onto the specimen that is placed on top of a grid. An electromagnetic projector lens will then produce an image that will then be focused and magnified by other electromagnetic objective lenses. The final image will be produced by a screen or photographic plate. As mentioned before, we get two fundamentally different electron microscopes, namely the transmission electron microscope or TEM and the scanning electron microscope or SEM. The TEM was first developed and differs from the SEM as electrons need to pass through the specimen to be viewed. This requires the specimen to be thinly sliced to provide us with an internal view. The SEM, on the other hand, gives a three-dimensional view of the specimen, as electrons are reflected off the surface of the specimen. This means that no internal structures will be seen. There are some key differences between the photomicrographs of different microscopes. Here we have a photomicrograph of a transmission electron microscope. The specimen is thinly sliced and stained using a heavy metal. These metals will bind to different parts of the cell and provide more contrast, as the electrons cannot move through these heavy metals and will not move to the fluorescent screen. Imaging using a TEM are usually in grayscale, but colored images can be obtained by using a technique called polarized light microscopy, where minerals with different refractive properties are used to alter the optical path of the electrons. We then have a photomicrograph using a scanning electron microscope. The SEM produces a three-dimensional image where all parts are in focus. This is because the image is produced by electrons on a screen and not our eyes that can only focus on a certain depth or dimension at a time. There are some practical components of microscopy that are very important. The first of these is the units that we use to measure the specimens. Most of the time we will be using micrometers, nanometers, and millimeters, but it's very important that we are able to convert between these, especially when doing magnification equations, as all the units in the equation needs to be the same. The easiest way to do this is by using a conversion scale. Let us look at an example. If a bacterial cell is 5 centimeters when magnified, but the actual length of the cell is 4 micrometers, what is the magnification? Firstly, we will need to convert 5 centimeters to micrometers using our scale. So on our scale, we can see that we would need to multiply by 10,000. We can then use our equation m equals to I over a to calculate the magnification as 12,500 times. The second practical component that we need to be able to do is know how to use a stage micrometer and eyepiece graticule. Now these two are used to measure the size of the specimen under the microscope, as a ruler would be too big. Now the eyepiece graticule is a disc placed in the eyepiece with 100 divisions. To be able to calculate the size of the divisions, we use a stage micrometer. If the stage micrometer has divisions that are 0.1 millimeters or 100 micrometers apart, and there are 40 eyepiece graticule divisions between the two divisions of the micrometer, each division will be equal to 2.5 micrometers. We get this by dividing the 100 micrometers by the 40 division.